Welcome to the video lesson on polarity. Before we begin, I want to define polar and nonpolar because I actually forget to do it in the PowerPoint, and that's sort of really important. So in covalent bonds, electrons are shared as we've been drawing Lewis dot structures, and there's two ways electrons can be shared. They can be shared evenly or unevenly. Okay, when electrons are shared unevenly or unfairly, the bond is said to be polar, and one of the atoms has more of the electron. If electrons are shared evenly in a bond, the bond is said to be nonpolar. So again, we have polar, which is when electrons are shared unevenly, and we have nonpolar, which when electrons are shared evenly between the two atoms. So how do we determine polarity? Is we use electronegativity, and as we've discussed, electronegativity is the ability of an atom to attract electrons to itself. It's measured on a scale of 0 to 4, and you have to remember from our electronegativity trends that it increases as you go higher on the periodic table and as you go more to the right. Okay? To determine the polarity of a bond between two atoms, you compare the electronegativity of the two atoms. Okay? And as a cutoff, the cutoff is greater than 0.4. So if you subtract the electronegativity between the two atoms, and it's greater than 0.4, then the bond is said to be polar. So here we have HF. Okay, we're missing the lone pairs, but who cares? And then the electronegativity of hydrogen is 2.1, and the electronegativity of fluorine is 4.0. If you subtract them, you get 1.9, and that's greater than 0.4. So that means this bond is polar. And why this bond is polar is that there are two electrons in this bond, and because fluorine is more attracted to electrons, okay, it pulls on the electrons more. So it has more of the electron pair than hydrogen does. As a result, as you can see on the bottom, fluorine gets a partial negative charge, and hydrogen gets a partial positive charge. And again, the reason why fluorine gets a partial negative charge in this case is that it has more of the electron pair. We talked about this a little bit, this symbolization over here. This arrow is called the dipole moment. Okay, and atoms that are polar have a dipole moment. Okay, the dipole moment, when you're drawing a dipole moment on a bond or on a molecule, okay, is an arrow, and the arrow points towards the more electronegative element, or towards the atom that has the partial negative charge in bond. So as you see what it says down there, that's kind of just saying what I said in words. F gets the partial negative because it has more of the electron pair, and the dipole moment points towards the more electronegative atom. Okay, so polarity is a continuum. Okay, we have cutoffs, but there are some molecules that are completely nonpolar, and there are some that are sort of between polar and nonpolar. And no bond is actually truly, completely covalent. It could also show ionic character. Okay, so it's important to realize that bonding is sort of a continuum. Yes, we classify things and have a cutoff, but there are some things that behave in between polar covalent, where electrons are completely shared, and in between ionic, where electrons are transferred. Okay, so that's just sort of a side note. Okay, so we talked about polarity. And some things are more polar than others and have a larger dipole moment, okay? And again, if there's a greater difference in electronegativity, the bond is more polar. The AP exam likes to ask questions, which bond is the most polar? So if we remember, we have, all of these atoms are H bonded to something in group 17, which is a halogen. And as we remember, as we go down a group, F is the highest and I is lowest, and electronegativity decreases. So if we see as we go across, we go down, okay, the dipole moment decreases, the bond gets less and less polar, and we can also see that the electronegativity difference decreases between the two atoms. So HF, if you subtract H from F, the electronegativity is 1.9, and the dipole moment, which is measured in Debye's, okay, and is measured experimentally, which we're not going to get into, is 1.82. When you go all the way down to HI, the electronegativity difference is 0.4, and that's basically nonpolar, and the dipole moment is 0.44. Again, so they like to show dipole moments in charts, and the point is the greater the dipole moment, okay, the more polar the molecule is. Now, And then that says bigger the dipole moment, more polar the bond. Okay, so here, this is an example of a question that they may ask. Okay, so in each group, circle the bond that is the most polar. Okay, well, we just saw from our investigation of the halogens on the last side that HF is the most polar. Okay, now here, this one may be a little bit more difficult because on the AP exam, they're probably not going to give you electronegativity values. So you're going to have to go based on the trends. And you need to remember, okay, one of the things that you need to remember is that F, O, and N are the most electronegative elements. Their electronegativities are pretty close to each other. Okay, so when we want to know that the bond is the most polar, okay, we want to know that one that has the biggest difference. Okay, well, I just said that O and N are very electronegative and have very close electronegativity, so this bond is not the most polar. Okay, now when we go between S and TE, if you look at your periodic table, S and TE are in the same group, and we know that as you go down, the electronegativity gets lower. So this is going to have the lowest electronegativity and the furthest away from O, which has a very, very high electronegativity. So this bond is going to be the most polar, and O will have the partial negative charge, and the dipole moment will point this way with the arrow going to the left. And this is just saying that, so in general, the AP exam will not give you an electronegativity table. So in general, you're going to assume that all bonds, okay, except carbon-hydrogen bonds, okay, when there are two different atoms, you're going to assume that those are polar unless the AP exam gives you other information. And again, to determine which one is the most polar, you're going to have to know your electronegativity trends. So here it says select the nonpolar bonds shown below. So I just told you that carbon-hydrogen bonds are nonpolar. And carbon-carbon bonds, since these are the same atom, it's also nonpolar. They have the same electronegativity, so they're sharing the electrons equally. And this is also a carbon-carbon bond. This is a carbon-carbon double bond, but they're still saving the electrons evenly. So this one, and this one are the nonpolar bonds where electrons are being shared evenly. Okay, we were just talking about bond polarity, when you have a bond between two elements or atoms. The way you determine the polarity of larger molecules is different from polarity, and this is about symmetry of the molecule. Okay, so if we take a look at these three molecules, okay, so the bonds here are carbon bonded to oxygen, carbon bonded to fluorine, and oxygen bonded to hydrogen. All these bonds, individual bonds, are polar. Okay, because like I said, when the AP exam gives you atoms, you don't get electronegativity tables. But you can assume that if it's not a carbon-hydrogen bond, okay, and it's not two of the same atoms bonding together, okay, that the bonds are polar. Okay, so if we take a look at the, I need the pen. Take a look at this molecule. Okay, so this bond is polar. Okay, O is more electronegative than C, so the dipole moment points this way on this atom. Same thing here, same bond. So O is more electronegative than C, so the dipole moment points that way. Now, if you notice, these dipole moments are pointing in opposite directions. Okay, as a result, the dipole moments cancel. Okay, and the molecule is said to be non-polar overall. It has polar bonds, but overall the molecule is polar. If you look at this guy, this is tetrahedral. Okay, so carbon bonded to fluorine. Fluorine is much more electronegative. So the arrows point this way for the dipole moment, down and over. Okay, now once again, you can see that for every arrow that's pointing up, one is pointing down, and for every arrow that's pointing left, there's one pointing right. So these dipole moments, you need to use that term, cancel, and therefore the bond is overall, or the molecule is overall nonpolar, even though it has polar bonds. Now this over here is our good friend water. Okay, so O is more electronegative than H. Okay, so the dipole moment points here on this bond, and here on this bond. Now notice, okay, these arrows are not pointing in opposite directions. Okay, they're pointing in the same direction. Okay, so therefore the dipole moments don't cancel. Okay, and this molecule of water is obviously said to be polar. Now the shortcut for determining something quickly, besides having to draw these dipole moments, okay, is to say if the molecule is symmetrical, both vertically and horizontally, then the molecule is nonpolar. Okay, and we see water is symmetrical this way. Okay, but not symmetrical that way. So that one is polar. So molecule polarity is about symmetry. Again, if the molecule is symmetrical, it's nonpolar. If it's not symmetrical, it's polar. And then, and that's because if the molecule is symmetrical, the dipole moments cancel. And if you remember in 10th grade chemistry, I said that the way to remember this is SNAP. So S-N-A-P, symmetrical, symmetrical, nonpolar. It's hard to write letters with the mouse. Asymmetrical, polar. Okay, so when deciding if a molecule is polar, okay, you have to, and this should be crossed out, I think, you have to draw the Lewis structure, look at the polarity of the bonds, okay, and then decide on the overall polarity of the molecule, and then place partial charges if they're necessary. So, for example, on this, which I should go back, this is overall nonpolar, so it should have no partial charges. So there should be no partial charges here. This is also overall nonpolar, so no partial charges, but this molecule is polar. Okay, so the more electronegative element, oxygen is going to get the partial negative, and the hydrogens, okay, are going to get the partial positive. Okay, where these are going to have no partial charges at all because the dipole moments cancel. So to do these, you have to draw them. Okay, and if I were you to maybe get some practice, because we're going to be doing this again when we come back, I would draw them, but I pre-drew them for us. Okay, so if we take, and we're trying to determine, again, if these molecules are overall polar or not. So once again, this has polar bonds, okay, because F is very electronegative, okay, and the dipole moments point towards the more electronegative element. You'll see once again after I draw them, this molecule is symmetrical, and all the dipole moments cancel. So this is nonpolar, and there'll be no partial charges. Okay, now this molecule is a little strange. Okay, I replaced the H's with the F's with H's. So now these bonds are nonpolar, so they don't really have a dipole moment. This dipole moment points up, okay, and this dipole moment points this way. Okay, now those dipole moments do not cancel. Okay, so this molecule is said to be polar, and the more electronegative atom gets the partial negative. Okay, now there's a way you could make this molecule nonpolar, is if you put the F over here and the H there, but and you wouldn't know this, so they would actually draw this one for you because you wouldn't know where to put the F's. But if the F was over here, okay, as opposed to here, then the arrow would go up here and down here, and then the dipole moments would cancel, and then the molecule would be nonpolar. Okay, but again, they wouldn't expect you to know where to place the F's. And then once again, we have this molecule. N is the more electronegative atom, so the bonds are polar. Okay. And the dipole moment is going to point towards the N because that's the more electronegative atom, and N is a very electronegative element. Okay, and then so these dipole moments cancel, but this one does not, so that makes this molecule polar, and then N gets the partial negative, and I'm not going to do it, but the H's, all the H's get the partial positive. So again, to decide on the polarity of the molecule, you have to draw it. So I drew it, and you can see that these two here, just to go through this a little, this is seesaw and that's T-shaped. These are not symmetrical. The bonds are polar, and they're not symmetrical, so they're overall polar. Okay, and in both cases, F is going to get the partial negative, because again, F is the most electronegative element on the periodic table. Now this shape is linear. And lone pairs don't matter, per se, because they're not pushing, but this is symmetrical. I know there's not an even number of lone pairs, but the atoms are the same on each side, okay? The dipole moment would point towards F here, and a dipole moment would push towards F here. Those dipole moments cancel, so that one is nonpolar, and it doesn't get any partial charges. This is a table of all the shapes, excuse me. The ones that are checked are the nonpolar shapes, okay? One of the most important ones is this one. Okay, trigonal planar has what they call rotational symmetry. Okay, so people think it's polar, but they love to ask this one. Trigonal planar molecules are nonpolar. They love to compare them to the trigonal pyramidal ones, which are polar because of this electron pair here. And in these diagrams, X are bonded atoms, A is the central atom, and E is a lone pair. Okay. So you kind of have to memorize the geometries, and I'm not going to go through each one. This one here, this one may look polar, okay, but these dipole moments point this way. There's two of them, okay, and this overall one cancels both of those out. Again, but it's easier to memorize, I think, the geometries and whether or not they're polar or not. And you can hear the checked ones are polar. This is the one you got to remember, though. They love asking that one. So why polarity is important is it affects the behavior of atoms. This red is a charged substance here, okay? Polar molecules are attracted towards charged substances, and non-polar molecules are not.